So I think I will prove this actually, because it's a result we use quite often, and it's not something I would ask you to do in an exam or anything, but it's a nice proof, and the result's quite important. So let me prove it. And we'll be practicing our understanding of the order of an element, and we'll be using a bit of number theory. So I'm trying to prove that the order of a to the s is this quantity on the right-hand side. So to start with, we don't know what the order is. We're going to prove it's equal to n over the greatest common divisor of n and s. I think I've changed my m to an s, but never mind. So let's say q be the order of a to the s, and we want to show that q is equal to this right-hand side. And we'll write d to be the greatest common divisor of n and s, just for short. Okay, so we know what n and s are, so we know what d is. Then, if I look at a to the s all to the q, what do I get? Well, a to the s is some element of the group, and it's got order q. So a to the s all to the q must be the identity. In fact, q is the smallest positive power for which that's true, but certainly it is true for q. Okay? So a to the s is an element of order q, so a to the s all to the q must be the identity. Okay? So then, using laws of indices, we get a to the sq is the identity. But now I can look at this in terms of a. Remember, a is of order n, so we've got some power of a being the identity, so the power must be divisible by n by part 4 of the result we started off with 50 minutes ago. So n must divide sq. Okay, sq must be a multiple of n. So that's by part 4 of the result we started off with. Okay? So n divides sq. Well, what we really want to get hold of is n over d. So n over d must divide s over d times q. You might want to think about that. SQ is a multiple of n, so s over d times q must be a multiple of n over d. And notice s over d is a natural number because d is a divisor of s. And n over d is a natural number because d is a divisor of n. So usually when I've got two integers and I divide one by the other, I'm going to jump outside the integers, but d is a divisor of n, so n over d is still a positive integer, and s over d is a positive integer. Well, I've got to do one more step, and this is where I might want to use Bézout's lemma. Let me write down what I want to deduce and then show you why it's true. Although some of you may know the result that enables me to get this straight away. Basically, n over d and s over d are co-prime. Their highest common factor, their greatest common divisor is 1 because I've divided out by d. So if n over d divides this product and it doesn't divide s over d, because n over d and s over d are co-prime, then it must divide q. That's what I want to deduce. And I'll just explain why that is in a second. But my bottom line for this page is going to be that q is a multiple of n over d. Remember, I'm trying to prove that q is equal to n over d, but we've got some progress here that q is a multiple of n over d at least. So why is that true? So Bézout's lemma says there exists, say, u and v integers such that u times n plus v times s equals d. Remember, d is the greatest common divisor of n and s, and Bezout says that I can write the greatest common divisor as some linear combination of n and s, where the coefficients are integers. So that means that u times n over d plus v times s over d is 1. Just dividing both sides by d, which is a positive integer. And this says that n over d and s over d are co-prime. Essentially, this number on the right-hand side is the greatest common divisor. So if I multiply this by q, I'm multiplying both sides by q now. Okay. You might have forgotten what we're actually trying to do. We know from here that n over d divides s over d times q. So s over d times q is here, and n divides that. Sorry, n over d divides that. So n over d divides this, but n over d certainly divides n over d. So what we've got is that n over d divides both terms on the left-hand side, so it divides their sum. Okay, so n over d divides the left-hand side, so it must divide the right-hand side. So that's where Bezout's lemma was used. So I'm not expecting you to be able to think up this proof straight away. It does involve a bit of getting it right, but you should hopefully be able to follow it, perhaps after rereading it once or twice. So what I said for this page is indeed true. So we've used Bezout's lemma to get this. So what we're trying to do, just to remind ourselves, we're trying to show that q is n over d, and so far we've got that q is a multiple of n over d. So what I want to do now is to show that n over d is a multiple of q, and then we'll have what we want. Also, suppose I look at a to the s to the power of n over d. We've got to be careful, a bit careful, because we've got to make sure that everything, all our powers are actually integers. But remember, d is the greatest common divisor of n and s, so in particular d is a divisor of n, so n over d is an integer. It's a positive integer, in fact. So it does make sense to take a group element to the power of n over d. Remember, we can only take group elements to the power of integers. So n over d is an integer, and I'm going to compute this using index laws again. Well, just rearranging the exponent using arithmetic in the integers, I can write this as a to the n to the power of s over d. I've just swapped the n and the n and the s around. And again, d is a divisor of s, so s over d is a perfectly good positive integer. Well, it's not necessarily positive, sorry, because s isn't necessarily positive, but it's certainly an integer. But now you see we've got a to the n. And what do we know about a to the n? Remember, a is of order n, so a to the n is the identity element. Good. So that's since n is the order of a, and the identity to any power is the identity. So So what we've proved is that a to the s, which is the element whose order we're interested in, all to the power n over d is the identity. But now we use part 4 again of the original result. Notice how we're using part 4. We've used it once already in the proof. So the order of a to the s, just think of it as b or something. The order of this element is q, and we've got some power of it being the identity, so the power must be a multiple of q. So n over d must be a multiple of q. But we've already got q a multiple of n over d, and since they're both positive, they must be equal. So let me say that. So hence, by part 4 again of the result, we've got that q divides n over d, because we've got something of order q raised to a power being the identity, so the power must be a multiple of q by 4. So now, using both results, which is that n over d divides q and q divides n over d, we get q equals n over d. So if one integer divides another and the other one divides the first one, then they must be plus or minus of each other, but since these are both positive, they must actually be equal. So i.e., remember q was the order of a to the s, and d was just shorthand for the greatest common divisor. So we've proved our result. So it was pure number theory, pure basic number theory. And the only group theory ingredient was the definition of order. So cyclic groups is one area of group theory where there's number theory coming in. So you will need to read through that proof again, I think, just to make sure you understand it. And you may want to just look up a little bit about Bezout's lemma, because I haven't proved that. It comes out of the Euclidean algorithm for finding the greatest common divisor. Did anybody do the Euclidean algorithm at school or college? So just an algorithm for computing the greatest common divisor of two integers. So it might have been in a discrete maths module perhaps or something, but it depends which syllabus you did. Anyway, so that was the proof of that. So let's just do a quick example of that. Well, let's go back to our I, which is still wandering around the complaint. Well, hopefully not wandering too far. Let's use our formula to work out something which you could just do by hand, but just to see the formula working. So the order of I is 4. Well, I might as well call it I rather than A. What about the order of, say, I squared? Well, we can use our formula, or we could just do it by hand. Using our formula, that should be 4 over the greatest common divisor of 4 and 2. Just using our formula, which in fact we have proved, so we can use it without feeling we're committing any sins. What's the greatest common divisor of 4 and 2? 2, yeah. So that's 4 over 2, which is 2. But we could do it by hand, because I squared is minus 1, and minus 1 definitely does have order 2, because the powers of minus 1 are plus 1 and minus 1. Those are the only powers we get. It's got order 2. The first positive power for which we get back to the identity is 2. So that does match up, as we knew it should do because we proved the formula. What about, since we're dealing with I, let's look at another example. What about, well, let's make it a bit more interesting. Let's look at I to the power 13. We can use the formula, so it should be 4 over the greatest common divisor of 4 and 13. Just plug in the numbers in. And what's the greatest common divisor of 4 and 13? 1. Good. 4 and 13 are co-prime. So in fact we get 4. So I to the 13 has got order 4 as well. And again you can check that because in fact I to the 13 is the same as I in fact. Because I to the 13 is I to the 12th times I. Or we can use our result from earlier that we just have to look at the remainder modulo 4, and when you divide 13 by 4 the remainder you get is 1, so this is just I again. Okay? So that's some examples of using our formula. But this works in any group for any element. Any element of finite order. Right, well I want to move on to one or two more results, and I'm not going to do all the proofs. And we're heading for this big result. So I'm going to state 2 or 3 more results. I'm going to prove one of them, and then we're going to have the big result at the end. That's the intention. And that'll pretty much conclude our discussion of cyclic groups for the moment, apart from what we will obviously be discussing them again in the tutorial next week. So let G be a group. Let A be an element of order n, so finite order n. Well, we've just computed the order of A to the S. Now we're actually going to look at the group generated by A to the S. So we already know the order of this, but we can actually say what the group is, and what the result is. And this is an easy consequence. I mean, you could even call it a corollary of what our previous result. And this turns out to be quite important. So S here is, sorry, I should have said what S is. S is an integer. So if we take any power of A, we can look at the group generated by that. Okay, there's nothing wrong with doing that. A to the S is just some element of the group. We can look at the subgroup generated by A to the S. And what this tells us is, all we need to do is look at the greatest common divisor of n and s. So this is actually a divisor of n. So we get all subgroups generated by powers of A just by looking at divisors of n. And that's quite important, it'll turn out. Well, I'll do the proof very quickly. I want to prove that 2 sets are equal, and the way I'm going to do it is show that one is a subset of the other, and the fact that they've got the same number of elements. They're both finite sets, so if one is a subset of the other and they've got the same number of elements, they must be equal. Well, as I say, I'm going to do this very quickly, and I'm kind of expecting you to read through it. Since the greatest common divisor of n and s, so it's certainly a divisor of s, so s is some multiple of the greatest common divisor, so every power of a to the s is also a power of a to the greatest common divisor. So this left-hand set is a subset of this one. Okay, every power of a to the s is also a power of the greatest common divisor, so everything in the left-hand set is also in the right-hand set. I mean, you'd probably want to write one or two more lines down. So certainly the left-hand set is a subset of the right-hand set, but they've got, the two sets have actually got the same number of elements. Why is that? Well, we can use the result we've just proved. Let me just call this D for a minute again. What's the size of the left-hand set? Well, that's the order of a to the s, which we know is n over d. Right, that's from the previous result. It's n divided by the greatest common divisor of n and s. But since d is a divisor of n, I could write d as the greatest common divisor of n and d. I mean, you wouldn't want to do that usually, but it's useful here. So what I'm saying is, d is a divisor of n, so the greatest common divisor of n and d is actually d. So we add that, for instance, with 4 and 2. So I'm writing d as the greatest common divisor of n and d, but what's this? By the formula in the previous proposition again, this is the order of a to the d. Just using the formula again. So what we've got is the number of elements in the left-hand set, which is this, is actually the same as the number of elements in the right-hand set, so they must be equal. If you've got two finite sets, one of which is a subset of the other, both got the same number of elements, they must be equal. So that was quite quick, but notice how we're building on previous results. And the importance of this is, as I said, you can compute the cyclic subgroup generated by any power of S just by looking at powers where the power is a divisor of n. So we only have to look at divisors of n, which gives you a lot more control over the situation. Because given n, say n equals 24 or something, we can look at all the divisors of n, and those are the only ones we're going to have to look at to compute these cyclic subgroups. So that's the significance of this result. Now we come to, I'll perhaps call this a theorem. Now I'm going to restrict my attention to cyclic groups. So the whole group is cyclic. It's generated by a single element. And let's take a subgroup of G. Then H is also cyclic. This is a very important result. So if we've got a cyclic group and we look at subgroups of that cyclic group, then every subgroup is also cyclic. So this is kind of saying that you don't jump outside the class of cyclic groups when you look at subgroups of cyclic groups. So a subgroup of a cyclic group is cyclic. And the general flavour is that cyclic groups are very simple groups. And so if we've got a cyclic group, then the subgroups can't be too complicated. They're cyclic as well. So I'm going to prove this in full. It'll remind us a bit about subgroups and also be using cyclic stuff. By the way, this group doesn't have to be finite. It could be an infinite cyclic group. It could be something like the integers. We don't need to use any finiteness. Well, G is cyclic. So suppose G is generated by A. Must be generated by something to be cyclic. A could have infinite order or it could have finite order, depending whether G is infinite or finite. So G is the set of all powers of A. And I want to show that any subgroup is cyclic. So let H be a subgroup of G. Remember our notation for subgroup, we use the less than or equal sign. Well, it's possible that H is trivial, it's just got the identity element, so let's just deal with that case first. So suppose H is the trivial subgroup. Well, that is actually cyclic because it's a subgroup generated by the identity element. Remember, any power of the identity is the identity. So the identity subgroup, the trivial subgroup, is cyclic. So that's okay. So if H is trivial, then it's cyclic. So the more difficult case is when it's not trivial. So now suppose H is not trivial. I want to show that H is cyclic. Well, H is a subgroup of G, so in particular it's a subset. So H consists of powers of A. Every element of H is a power of A, because everything in G is a power of A. Then, say A to the S is in H for some S non-zero. So we're assuming that H is in the identity element. So there must be some power of A in there where the power is not 0. Okay? Now, S could be positive or negative, but since H is a subgroup, A to the minus S, which is just A to the S all to the minus 1, will be in H. H is a subgroup, so if A to the S is in H, then its inverse is also in there. That's part of the subgroup criterion, which is A to the minus S. And the reason I've written this down is I want to find a positive power, but since S is non-zero, either S or minus S will be positive. So S could have been minus 7, but that doesn't matter because then I could use A to the minus 7. So what this shows is some positive power of A. Either A to the S or A to the minus S is a positive power of A. And now I'm going to take the smallest positive power of A that lives in H. It contains a positive power. So it might contain A to the 7th and other things. I'm going to take the smallest one. So let, say, M be the smallest positive power that lives in H. Okay? So I'm going to take the smallest K, such as A to the K is in H, and I'm going to call that smallest one M. M for min, if you want.